Hello everyone, welcome to Graphing Radical Functions. So, first thing we're going to do is we're going to learn to identify radical functions on a graph, and we're going to talk about the key features, and we're going to go from there. So, then we're going to apply transformations to graphs of radical functions. We've done this with polynomials, quadratics. We're going to learn how to do transformations on these. Then we're going to determine the equation of a radical function based on the graph. In other words, we're going to take a graph, we're going to pick a couple points, and we're going to be able to figure out the entire equation from the actual graph. And then we're going to interpret those graphs in order to solve problems. All right, so let's start off. What is a radical function? Well, let's go ahead and look at Desmos, right? Because the first thing we're going to do is compare f of x equals the square root of x and f of x equals the cube root of x. So let's go ahead and go to Desmos, and I've pulled up both of them here. So you'll notice, if we zoom in a little bit, that first of all, this green one is x squared, right? And then this purple one is x cubed. Now you'll notice here that the x cubed function actually goes down into the negatives, whereas the x squared doesn't. And that actually makes a lot of sense if you just apply numbers to the situation, right? In other words, let's plug in, let's start with 4 for the first one, right? Y equals the square root of x. If we have 4 for x, then y is going to equal 2, right? But if we have negative 4 for x, we're going to have 2i, right? We're going to have some imaginary number. Imaginary numbers don't exist on this graph, right? This is strictly a real numbers plane. So when we look at this, you'll notice that it always stops when it hits 0, and that's because x can never be a negative number and produce a y value that we can use, right? So in other words, every time we have a square root function, it's only going to stay positive. And what's interesting about this is that's actually true for any even degree function, any even degree root function. So square root, fourth root, sixth root, those will all look like this. They'll just be a little bit more extreme, right? Because it actually, the higher the n for the root, the closer this is actually going to get to the x-axis, because it's going to take more to get farther, right? In other words, in order to make y2 for a square root, x would have to be 4, right? But in order to make y2 on a cube root, x now has to be 8. You see what I'm saying? It takes more just to get to the same number, the higher your n value goes. So conversely, if we look at our y equals the cube root of x here, this little graph, you'll notice that it does actually go negative. And that does also make sense, right? Because if you have the cube root of negative 8, right, the cube root of negative 8 is just negative 2. So answers for y can be negative, whereas they can't be negative on the square root. So that's why it kind of does that. All right. And you'll notice too, like I said, that the cube root, it actually pinches against the x-axis a little bit more. And that, that makes sense for this. Okay. All right, so let's go back. It's asking us, what are the domain and range of each function? Well, that's kind of what we were just talking about, right? The domain of our square root function, in other words, all the x values, well, it looks like the x values exist everywhere that isn't negative. So starting at 0 and going on, so where x is greater than or equal to 0 exists on our graph, right? So that's what we can put for our domain. So for the domain for f of x, it's where x is greater than or equal to 0, right? Okay. And now think about our range. In other words, our range are our y values. And you'll notice here that it kind of tapers off, but if we keep going, this is literally going to go up forever, right? It's going to go up forever very slowly, right? Because it's kind of the opposite in a sort of way of an exponential function. An exponential function rises very, very quickly, right? And we'll learn about that in Unit 6. But a square root function is gonna go up forever, but it's just gonna do so very slowly. So the range of the function, right, it can go up forever, but is it gonna go down forever? Well, not on square root, right? It stops at 0, just like it does. So just like it does for the range. So it's the same thing. The domain and the range are the same for square root function. All right, perfect. All right, so now what about x cubed? Well, hopefully you kind of get this idea, but the x cubed does the same thing, right? It's going to rise even more slowly, right, than x squared does, but it does go positive and negative forever. So we can actually just say the domain and range, and I'm just going to write this once for both of this, but it's essentially we go from negative infinity to infinity. I know I'm using different notations here, but when you use infinity, this is just easier. All right, the other way you could say it is like all real numbers, right? Like that is also true. Okay. All right, now you'll notice here, and I wrote this as a little note down here for you. Note that there are no minimums or maximums or asymptotes, right? We have specific points on our graph here, right? And these points don't go by the same names as before, right? There's not minimums and maximums. They have two points, right? One of them is known as an inflection point, right? And then so if we go back here, right? There's 2 points here, right? There is the inflection point, which is here. And the reason why they call it the inflection point on odd degree functions is because this is where it like curves, right? This is like the middle of the graph, essentially, if you want to call it that, right? And then the other thing they'll call it for even degree functions is they call it a starting point, because this is where the graph starts. It's kind of where it starts for both of them, but because it actually goes negative, they call it the inflection point for odd degree functions. So that's kind of the idea behind that. So if we go back up here, so yeah, there are no minimums or maximums or asymptotes. The only real values, or the only real terms you're going to want to know are starting point and inflection point, right? And the starting point is for the even, inflection point is for the odd degree functions. All right, so let's talk about transforming radicals. So when we transform a radical, we use this formula here. This should look pretty familiar to you, right? The only difference between this and when we were transforming others before is that now we have the square root thing, right? And remember that in here could be a 2 or a 3, right? So this could be either way. But essentially we have a equals the square or cube root of x minus h plus k. And a is still a vertical stretch or compression, and if a is negative, it reflects over the x-axis, just like it always does, right? This is exactly the same as it does before. H is a horizontal shift, and then k is a vertical shift, right? And remember that h moves counterintuitively. So in other words, if we have like x minus 4, it's going to move to the right, right? If we have x plus 4, it's going to move to the left. That's just kind of always how that works, right? It always kind of moves the opposite of the way we would think it would. And then for k, the k at the end is just going to move our graph up and down. All right. So let's go ahead and look at one of these, right? So what are the transformations to the parent function? So if we have f of x equals, and this is probably a good thing to write down here too. If we're talking about the parent function for this, right? The parent function for this equation here is just, we'll just call it f of x, right? Because that's probably why they did g. So f of x equals the square root of x, right? This is the parent function. That's it. All of these numbers are things we're doing to change the original function, right? That's why this is called the parent and this is called the transformed function. Okay. So we have 2 times the square root of x plus 3 plus 5, right? So the 2 is out in front. So the 2 is going to be our a, right? And our a is the vertical stretch or compression. So because it's a whole number and not a fraction, right? And because there's no negative, there's not going to be a reflection, and it's going to be a vertical stretch, right? The 2 makes it a stretch because it's a whole number, and the fact that it's positive means it doesn't reflect, right? And then the 3 in the middle here will actually shift it to the left, and the 5 will shift it up. So these are all the transformations of this graph. Vertical stretch of 2, shifted to the left 3, and shifted up 5. And if we take a look at this graph, I'll go ahead and get rid of these. If we look up here, right? If we take this graph here, right? Well, what point are we at here? Negative 3, 5. So you'll see our starting point, which would normally be there, right? You'll see our starting point actually moved 3 to the left and up 5, just like we said. And you'll also notice that it's getting extreme a lot more faster, right? Because this here kind of tapers off. This kind of goes up a lot faster, right? It actually goes up twice as fast, right? So this is a good way of showing you exactly how this graph transformed. Gives you kind of a visual of it. All right, so let's go and try with this. So if we have g of x equals negative 1/2 times the cube root of x minus 1 minus 3, go ahead and give that one a shot, see what transformations you come up with, and we'll pause the video, and we'll get back into it here once you're done. All right, so let's go and give this a shot. So first of all, we're going to talk about our A value. So let's just go and do this. So A is our vertical stretch. And in this case, it's actually not a vertical stretch, right? It's a vertical compression because this number is between 0 and 1. It's a fraction, right? So 1/2 is a compression by 1/2. In other words, it's going to get closer to the x-axis faster, right? It's not going to leave, but the numbers are going to be half the size, right? And then it's also a reflection, right? And it's a reflection over x-axis because this is negative, right? So because A is this, you'll notice it's negative. That's going to contribute to the reflection, and the 1/2 is going to be a compression, right? If it was a 2, it would be a stretch, but because it's a fraction, it's compression. All right, so that's A. That makes sense. Now we have x minus 1. Well, remember that in these kinds of problems, a negative actually moves it to the right, right? So now we have our h value, and our h value is going to shift it 1 to the right. And then finally, we have our k value. And k is minus 3, so we're going to go down 3. All right, so what we're saying is 1 to the right, down 3, and it's going to be closer to the graph, also reflected, right? All those things. So now let's actually just take a look at our function here. And I'll pull up the cube root function as well, just so we can kind of see it. Okay, so you can see that this kind of flips, right? Okay, and then our point of inflection, which was here, right, at 0, 0, is now over here at negative 1, 3. In other words, we went down 3 and to the right 1. And you'll also notice that if we were to shift this back up, you see how much like wider or taller this curve is, and this one gets very, it wouldn't be as tall, right? If it was flipped over, like you can even see on this side, it doesn't get as tall as fast, right? And the reason why is because it's been compressed by half. So it's actually half as tall, or it gets tall half as fast, I guess is the best way to put it. All right, perfect. So that's a transformation. Now, that was really nice and smooth, right? Because it started off in this form that we know. But what happens if it doesn't? Well, what do you think we got to do? We got to put it into that form, right? So, rewriting radical functions, sometimes we have to rewrite the equations so that they fit the form that we know, right? F of x equals a times the square root or cube root of x minus h plus k. So let's identify transformations, and let's start off with a relatively easy one. So let's say we have g of x equals 9x, all right? What we can do is, remember, we can break up this 9x into the square root of 9x equals the square root of 9 times the square root of x. And the square root of 9 is just 3, so this is going to give us 3 times the square root of x, right? So this here, this little piece of the function, is what we could then use to find our transformations, right? And the only transformation done to this would be the multiplying it by 3, right? Which means that it's going to stretch by a value of 3. Our a is 3 in this case, right? Yeah, the graph is stretched by 3. So let's try to do one together here, okay? So we have h of x equals the square root of 4x plus 16 plus 7. All right, so let's go ahead and jump into this. So the first thing I'm seeing is that the 4x is, like, it would work, right? But essentially what this is saying that we have the value of 4 times x, and then we're adding 16 to that, right? So if we break down the numbers inside the radical, we can pull out as much as possible, and that can kind of simplify the amount, or scale factor in this case, like the amount that we're increasing it by. So if I have 4x plus 16, all that plus 7, what I can do is I can take this 4x plus 16. I notice that I have a 4 that's in common between 4x and 16, so I'm going to factor out a 4. So I've got the square root of 4, and that's going to be times x plus 4, right? I factored out a 4 from each of these. So I have a 4 times an x, which would give me 4x, and then 4 times 4 would give me 16, right? And then this is just plus 7. All right, so now, because I have two things multiplied by each other, right, this is 4 times x plus 4, I can take the square root of each of them individually, right? So I can do this, so this will turn into the square root of 4 times the square root of x plus 4, right? And then all of this just plus 7. And now the square root of 4 is just 2, right? So this will actually give us 2 times the square root of x plus 4 plus 7. And if you'll notice here, this is exactly the form we had before, right? We have an a of 2, so in other words, the graph is stretched 2. It's x plus 4, so it's shifted to the left 4. Remember, that's counterintuitive. And then it's shifted up 7, right? Because the 7's over here. All right, perfect. So let's go ahead and try one. This one's a little bit tricky because you can't really take everything out, but as long as you take as much as you can out to make sure that the scale factor is affecting every number, you're doing everything you can, okay? So that'll just be kind of a hint. Go ahead and pause the video, give it a shot. We'll do it together. All right, so let's do it together. So j of x equals -2 times the square root of 12x plus 4. All right, so let's take out what we can. Well, I see here that we have a square root of 12x. So let's go and just start with, we're just going to work with that for a second, okay? Let's ignore the other numbers. So 12, we have a square root. So we have to find a square, a perfect square that goes into 12, right? My instinct is 4, right? That makes sense. So 4 times 3 is 12. So essentially what we're going to do is we're going to break this 12 into 4, which is 2 squared, right, times 3. So we can pull a 2 out because we have a 2 squared. This is from the last lesson, right? Okay, so we have, here we have -2, and then we can pull this 2 out, remember? So times 2. And then on the inside, we're still going to have this 3 and then x. Right? So all we did is we basically pulled 4 out, and because 4 is 2 squared, you know, it just comes out as a 2. And then plus 4. And this is going to lead us to -4 times the square root of 3x plus 4. Now, we can confidently say that, and this is where this is a little strange, right? If you got here, that's great, right? You did everything perfectly. The interpretation might not have clicked right away, but that's fine. Because we've pulled everything out that we can, and because this x isn't really being added to anything, we can actually say in this case that a, because a is just the number being multiplied by the x value, right? A is the multiplier. So we can actually say in this case that a is -4 times the square root of 3. That's actually what, like, that is what it's being multiplied by, right? Like, if you wanted to break this part down a step more, you could say this is -4 times the square root of 3 times the square root of x, right? Because you can break that down and then just all this plus 4. So you could see how 4 times the square root of 3 is our a value, right? Okay. And then, well, in this case, we didn't move it left or right, right? Because there's nothing being added to the x inside the radical. So the only thing left is 4, which in this case is our k value. So our k value just shifts it up 4. All right, now it's going to be kind of hard to quantify. Well, first of all, if a equals -4, or -4 times the square root of 3, this is going to be a whole number, right? So it's going to stretch by that value, right? So that's a stretch. The only thing I wanted to also call out is that it's negative, so it's also going to reflect, right? I just wanted to make sure that was clear. So let's go ahead and let's look at it on the graph, okay? So I have this one here popped up, and it's a square root, so let's go ahead and pull up our square root function. You can see that it's doing some really weird stuff, right? So first of all, we -2 12x, yeah, okay, we're on the right one. All right, so you'll notice first of all that it flips down, right? And then you'll also notice that the whole graph is shifted up 4, like we said it was going to, right? Because the original starting point is all the way up here at 4, 0. So we're starting all the way up here, and then you can see that it's stretching. It's stretching much faster. It's just upside down, so it's going down, right? So this seems like a reasonable answer. Okay. All right. So how to write an equation given a graph. So in other words, if they give us a graph, if they actually give us something to look at, how can we use that graph to determine what the equation would be? Okay. So I'm going to break this down to you step by step, and it'll make sense here by the end, I promise. All right. So step 1 is identify the starting inflection point and one other point. Okay, so I'm going to give you a graph here. Okay, let's give you this. Okay, So if we're looking at this function here, I'll back out a little bit. If we're looking at this function and we're trying to identify the graph, then we have to identify the starting point and the slash inflection point. In this case, if we look at our graph, right, it's a third degree function, so we're going to have an inflection point, right? So we have to identify our inflection point, and then we want to identify one other point, okay? So in this case, our inflection point is 3, 4, right? So you want to write that down. You want to write down 3, 4, and then the other thing you want to do is you just want to find some point that works. It looks like this would be a good point, and it is, right? So we can use 4, 6 as our other point. So you'll notice that what I did is I wrote down the inflection point as 3, 4, and I wrote down our other point as 4, 6, right? And we're going to need both of these because our inflection point is going to show us how the graph is transformed, right? If our inflection point is at 3, 4, that means this graph has been shifted 3 to the right and up 4, right? The inflection point is the cheat code to showing you exactly how that works, right? So this has gone over 3 and up 4. That's the transformation. In other words, we know that when we graph this, right, if we look at this, we can use these points to find A, right? The inflection point shows us the translations. It goes right 3 and up 4, which means to the right 3 is -3, right? And then up 4 will have this 4 out here. Now, the only thing we don't know is A, right? But we can find A as long as we have an X and a Y value. I wonder where those are going to come from, right? Well, if we look up here, right? Remember how I told you to find another point that you can clearly define? In this case, we were able to clearly define the point 4, 6. So what I'm going to do is I'm going to plug in a 6 for Y, a 4 for X, and we're going to go from there. So I plugged in the 6 for Y, I plugged in the 4 for X, and now we're just going to literally solve this equation for A, right? So if I have 6 equals A times the cube root of 4 minus 3 plus 4, right? Well, this is the same thing as the cube root of 1, right? 4 minus 3 is just 1. And the cube root of 1 is just 1, right? And A times 1 is just A, right? So a lot of this just kind of cancels out into just A. So this is going to equal 6 equals A plus 4, right? Which is, of course, going to give us A equals 2. And now we can use that to write the general equation, right? We know that the graph has been shifted 3 to the right. We know it's been shifted 4 up. And now we know that A equals 2, so we know the whole thing has been stretched by a factor of 2. That's it. All you have to do, like I said, the key takeaway is to find the inflection point or the starting point if it's a cube root or if it's a square root, right? And then we're going to use our other point to be able to plug everything in, solve for A, go from there. All right, awesome. So let's do one more problem. Let's do an application problem here. All right, so when Sasha looks out over the sea, the visibility in miles from a certain spot on the cliff can be calculated using the function d of x equals 1.5 times the quantity x plus 5, where x is the elevation in feet above sea level of the path. Sasha walks along through elevations ranging from 5 feet to 40 feet above sea level. Describe how Sasha's visibility changes as her elevation increases. So in other words, she's walking up this cliff, right? And she's starting at 5 feet above sea level, and she's going to end up walking up to about 40 feet above sea level. As she's walking up the cliff, she can see farther and farther away, right? And the distance that she can see is the total of d of x, right? So d of x is the distance she can see. X is how far up the path, how high above sea level she is on the path. Does that make sense? So the first thing I would do is I would just take this graph and I'd plug it in, right? Anytime you have a word problem, the graph is like our picture. So let's go ahead and plug it in. All right, so if we pop this up, right, and you'll notice here on Desmos, if you want to know this little trick, I put in the function here, and I also put in these constraints to tell us specifically between 5 and 40, right? And we're talking about the amount of feet above sea level, right? So at 5 feet above sea level and at 40 feet above sea level, this is the graph we're going to get, right? So it looks like this. Let me zoom out a little bit more. And as you can see, if she starts at 5 feet, right? So at 5 feet above sea level, she can see 3.8 miles, 3.87 miles, right? And then all the way over here, at 40 feet, she can see 8.2 miles. So she's able to see more as she gets the farther along up the path she can see farther in the distance, right? And now what's the question asking us? Describe how Sasha's visibility changes as her elevation increases. In other words, as this number goes up this chart, how is it increasing? Well, there's two ways we can basically solve this problem. one way is to kind of just talk through it, right? It doesn't ask us for any specifics necessarily, but I'm going to show you two ways that you could explain this. The first way you could explain it, and this is a little bit more of a, you'll talk about this stuff more in calculus, but you'll notice that as it goes along, the amount that it's increasing is actually decreasing. I know that sounds weird, but like it actually, you can see a lot more from 5 to 10, right? The distance that you can see increases a lot more than the distance from 10 to 15, right? You're still seeing more, but you're seeing less of that more, if that makes sense. So the rate of change is slowly going down, right? It's not a constant rate of change, right? This isn't a straight line. So the rate of change is going down over time, right? And that's kind of the case for all radical functions. So if you wrote that down, that would be a reasonable answer, right? Because it doesn't ask you for any specifics. But if we wanted to get more specific, right, it says here, describe the visibility changes as her elevation increases. Well, another way we could always refer to this would be to refer to the average rate of change, right? Because if we can look at an average rate of change, that will tell us approximately like, oh, when she goes up 1 foot, she can see this much more, right? That's exactly what this rate would help us with. So what we're going to do in this case is just kind of talk about the average rate of change, right? Well, the average rate of change is a line. Hopefully you guys remember from like algebra 1, if you have like a point here and a point here, right? Our graph looks like this, right? It's kind of curved. I know it's bad, but you get the idea. If we draw this straight line through, right, that's the average rate of change, right? In order to find the rate of change, well, what is the rate of change? It's our m, it's our slope, right? So all we have to do is find the slope of this point here, right? Here, I'll switch the color. We need to find the slope of this point here and the slope of this point here. Now, we need to find the slope of those 2 points. So how do we find the slope of 2 points? Well, hopefully you guys remember the little trick here. So let's write down the points here. So we have 5, comma, I'm just going to put 3.9, right? Let's just do that. So we have 5, comma, let's just do 3.8. Let's just round it off. So 5, comma 3.8 is this point right here, right? And our other point is going to be, what, 40? So 40, comma, let's just say 8.2. Sound good? So 40, comma 8.2, right? And now we use Desmos to make this easier, right? But if we didn't have Desmos, if I know that x is 5, I can actually, I can take this value of 5, I could plug it in right here for x, and I'd get 10 times 1.5, and then I'd take the square root of that, and I'd get 3.8, right? So we can always plug in our points to pop out numbers. So if you don't have Desmos, you can still plug them in and figure it out. And now we're just going to use the slope formula, right? So in other words, if we have, well, y2 minus y1, so 8.2 minus 3.8 over x2 minus x1, so 40 minus 5, right? If you plug that into a calculator, 8.2 minus 3.8 gives us 4.4. 4.4 over 40 minus 5 is 35. So now we do that. 4.4 divided by 35 gives us 0.13, we'll say. So now this is the important part, right? This equals, it doesn't actually equal it, but it's close. All right, so 0.13. So what this is asking us is, how does her visibility change? Well, it looks like for every foot we increase, right? For every foot that she walks along this path, she can see another 0.13 miles than she could before, on average, right? Of course, it's not a straight line, right? But on average, she can see 13 1/100ths of a mile more than she could during the last foot. All right, and that's it. So just a quick recap, what we did is we started off by defining our radical functions, square root and cube root. We then learned how to transform them if they're in this nice pretty format. If they're not in that pretty format, then we rewrote that, and we changed it into that pretty format, right? And then we figured out how to take an actual graph, use the point of inflection and another point in order to find what the actual equation would be. And then we kind of just did a little application problem where we used the square root function in order to figure out Sasha's ability to see a little bit farther. By the way, this is the greatest drawing of all time. All right. That's awesome. I will see you guys in the next video.